What is the biggest takeaway for you? One line only. Don't summarize like the 25% mistakes are made in voltage drop and voltage gain, 25% mistakes are made in this or that. Exactly. Know the fundamentals. FE exam is fundamentals of engineering. Don't take shortcuts. You might pass FE exam with some strengths, some weaknesses, but some of these topics, guys, circuits, electronics, power, it would be to your disadvantage if you sort of pass the exam, FE exam, barely, and then walk into PE power, and then we are over there talking about fault analysis, per unit system, symmetrical components. So this is the type of discussion I have in my live training program. KCL. You're gonna see me stuck on this slide for at least 5-10 minutes. Okay. And you're gonna be like, Wasim, what the heck? Move on, right? We've seen this slide in on demand. What is a big deal about it, right? The reason is that KCL, KVL, guys, forms the basis of circuit analysis, okay? If we gloss over this, it's gonna routinely come back and bite you, okay? So I'm not gonna derive it. I'm gonna look at it from the equation standpoint. I'm gonna look at it from the actual network standpoint, and some of what we call, not assumptions, but notations, okay? That what is our conventional current, okay? What is considered a voltage drop? What is considered a voltage gain? When I present the voltage gain, voltage drop, polarities in isolation, everybody is, like, I know this inside out, right? But then to put it in practice during circuit analysis, that's where you get to see the real application, okay? That's where students fault. That's where they fail, okay? So KCL, it's very, very intuitive. What it is saying is that the sum of current is always equal to 0, okay, at a given node. So the other way to look at it is that the total current that is entering a node must be equal to the total current that is leaving the node, okay? The way I construct my equations for KCL, there are multiple ways to do them. You guys have seen that in the on-demand course. The way I construct my equations in KCL, I collect all the currents that are entering into a node on the left-hand side, and I collect all the currents that are leaving the node on the right-hand side, so that you don't have to really worry about plus and minus and plus and minus and so on and so forth, okay? It is based on the law of conservation of charge. Very simple. So far, it's very intuitive. It might almost seem like a waste of your time, right? Now, the issue arises when we put it into practice, okay? So let's look at this voltage drop. Let me ask you this question. Will there ever be a voltage gain across a resistor? I'm going to repeat. Will there ever be a voltage gain across a resistor? No, it's a big no. Resistors will always have voltage drop. All right. Yeah, I square R losses are going to come into play. Heat is going to, energy lost and whatnot. So remember that there will always be a voltage drop across the resistor. All right. See, some of you guys, and again, I'm not judging everyone. It's it's a it's a learning environment, right? So don't feel shy thinking that, I'm going to look bad. Nobody knows who anyone else is, and I don't judge my students. The whole point is learning. I would rather have you make all the mistakes right now and no mistakes in the exam, okay? But the point is that some of you did stumble, right? Voltage drop will always happen across a resistor, okay? Now, there's more to it. The node that the current enters into a resistor, okay? We basically note it as a positive terminal. Current enters the positive terminal of a resistor and leaves the negative terminal of the resistor. Is that clear? Now, in some of the analysis, some of the practice problems that I've done, I've actually used this notation. I've done positive, negative, going through the resistor, entering the resistor, leaving the resistor, all of that sort of stuff. For the most part, it's so intuitive that at least I tend to skip marking the polarities of the resistor. Okay. Generally speaking, if you have intermediate level of understanding, or if you're a beginner in circuit analysis, or you tend to make mistake, I would say mark the polarity, right? It just takes less than a second. But the other reason is sometimes it gets a little bit cluttered. The circuit becomes a little bit cluttered. So multiple reasons, but definitely mark the polarities for voltage. Now, voltage, it's obvious, a voltage gain can happen and a voltage drop can happen across a source. The gain is pretty intuitive for most of the students. The drop is not intuitive for most of the students. This results in, again, I don't have any hard stats, but just based on eyeballing and, the number of questions I see from students and mistakes that students make, I would say about 20 to 25% of the mistakes in circuit analysis are due to this one simple misunderstanding. Okay. Students arbitrarily, decide whether it's going to be a voltage gain or a voltage drop. There's method to this madness. Okay. Voltage gain, guys, is only going to happen. And hopefully with a couple of practice problems that we're going to do, we're going to encounter this. Voltage gain only happens when current leaves the positive terminal of the battery and enters the negative terminal of the battery. Over here, this big bar is the positive terminal. The small bar is the negative terminal. The direction of current. Now, you'd be surprised. Some students, even when I draw it like this, they're not able to follow that current is actually leaving the positive terminal and entering the negative terminal, right? Everyone can see that. So from the standpoint of the positive terminal, current is actually leaving. From the standpoint of the negative terminal, the current entered the negative terminal. You guys can see that. If I break up this big arrow into two small arrows, is that obvious? Is it clear? Right? But some students are like, no, Wasim, what about if I hide this negative terminal, then this arrow is going to hit the positive terminal, right? So that much understanding, guys, we need to have, right? We need to be able to, again, FE covers your entire undergraduate engineering. If you guys don't realize it, the course that I have prepared for you basically is a crash course on your 4 years of undergraduate electrical and computer engineering, right? That's what it is. I've basically taught you 4 years of undergraduate engineering in one course, right? So make sure you're paying attention, right? And you're reflecting, you're trying to absorb. Okay. So this is obvious, right? Voltage gain is happening when the current is entering the negative terminal and leaving the positive terminal. Now, when students see a voltage source, they are not able to comprehend that this particular voltage source can actually be voltage can actually result in voltage drop in the circuit. Okay. Let me give you one quick example, and that would make sense. And then I'll discuss, the conventional current direction and all of that. If I have one voltage source over here, right? One resistor over here, another voltage source connected like this. Okay. Resistor V1, V2. Now think about it like this. V1, positive, negative, positive, negative. And David, we will have, at least 2-3 examples. I'm not going to convert this into a full-blown, a 2.5 lecture that I do for my live training, but will basically cement the concepts that I'm trying to explain, right? I do about 10 to 15 practice problems using the homework assignments during my live training. Right now, I'm going to go through a couple of practice problems using the on-demand course content. But let's come back to this. So what we have over here, no, I'm not asking for equation. Forget about the equation, right? When we look at the way I like you to understand this, and visualization is a big deal, right? Guys, when you're solving the circuits, sketching them out is super important. But imagine that that V1 is basically shooting current, right? In this direction. V2 is also shooting current in this direction because current basically leaves the positive terminal of a battery and enters a negative terminal. If I short a battery, right? Short a battery, it will basically be pumping current out of its positive terminal and it will be coming back to its negative terminal. Make sense, right? So just visualize V1 is shooting I1 in this direction and V2 is shooting I2 in this direction. Now, if I1 is greater than I2, that would basically mean that V1 will be greater than V2, correct? Now, if I1 is greater than I2, then the net current will basically be this, right? And it will be I1 minus I2 that will be flowing through the resistor, correct? That is easy. It's easy peasy, right? Lemon squeezy, not a big deal. Everyone can see that. If my V1 is greater than V2, my I1 is going to be greater than I2, right? And current will basically flow from V1 to V2, right? So let's say this guy is it's a 10 volt battery and this is a 1 volt battery. Make sense? Now the issue arises. So the way that I'm going to write this equation, right? In this case is going to be, so let's call it 1 ohms, right? I'm going to say that, okay, so the net current, let's call it I, right? So I is circulating, right, throughout this loop. So this I is going to go through the resistor, 1 ohm resistor. So it's going to be a voltage drop. So on the right hand side, I have a 1 ohm resistor, right? And I have the total current, which is 10 volt minus 1 volt divided by 1 ohm. Correct, right? There's basically the voltage drop across the 1 ohm resistor, right? So this is the current I. This is the resistor R dot I. Everyone can see that on the right hand side. Yes, no, maybe. Everyone can see that, guys. If you guys have questions, please ask. And please use everyone in the drop-down menu when you're participating. A lot of students are using host and panelist. I can see it. That's fine. Others cannot. Okay. Now the question is, what happens with this V2? What happens with V2, guys? When this current enters the positive terminal of our battery, V2. what happens? How are you going to write it? As a voltage gain or a voltage drop? Voltage drop, right? So if right-hand side is where I'm accumulating all the voltage drops, am I going to write it as a negative voltage on the right-hand side or a positive voltage on the right-hand side? Negative voltage on the right-hand side. Okay, let's see. So -1, right? Okay. What about the left-hand side, guys? So this current is traveling. It hits the negative terminal, leaves the positive terminal. Is it a voltage gain or a voltage drop? Voltage gain, right? We're going to write it on the left hand side, yeah, as a positive 10 volts or a negative 10 volts. Positive 10 volts or negative 10 volts, guys, quickly. Positive 10 volts. Okay, so let's take a look at it. Okay, I'm going to erase everything over here, and you guys by consensus have developed this equation. So let us analyze this equation and see whether this equation is right or wrong. I'll tell you that this is wrong. Okay, this equation is wrong. How? 10 volts is turning up to be 1, 1. So this is 9 volts. 10 minus 1 is 9. Then you told me that I'm going to subtract 1 volt over here. So 10 volts is becoming equal to 8 volts. You guys see any issue here? What's the problem? Can somebody tell me what's the problem here? It's one of the simplest circuits that you can see. One resistor, two voltage sources. And the only thing I'm trying to explain you is voltage gain and voltage drop. Can somebody spot where we went wrong? Quickly, guys. We have more advanced practice problems to work with. Polarity of V2 goes through the positive. Yes. Why? On the right-hand side. Why? This should have been positive, right? Why should have been positive? I told you that when I am collecting all the VGs, voltage drop gains on the left-hand side, I'm going to write them as is, positive. When I'm collecting all the VDs, voltage drops on the right-hand side, I'm going to collect them as positive. So this was a positive. This will be a positive. See, now it makes sense when you compare it. And again, also learn how to check your work, okay? That something was off, right? If you're working with variables, it might not be that obvious, okay? So all the voltage drops on the right-hand side, all the voltage gains on the left-hand side. And it's basically, circuits 101. Is that clear? Does it make sense? So I would say 90% of you, maybe even higher, got this one practice problem wrong, and it's one of the simplest problems. I'm not trying to shame you, okay? I'm just trying to tell you that circuits is deceptive. I intentionally selected KCL and KVL because I could have gone and selected more advanced topic like Thevenin or Norton or maybe superposition or maybe source transformation, but it all starts even before circuit analysis starts really from Ohm's law. Okay, is this clear, guys? What we ended up doing over here, how this voltage drop came into play, right? And how we were able to handle it, right? Again, the point is not to sort of to expose your weaknesses. Might as well learn it right now and make mistakes. So we keep the voltage gains on the left, and yeah, either or. You can do it either or. The other way, I'm going to show you quickly. Let's see if I have more space. Well, we're going to dive into the circuits very quickly. Another way, there are multiple ways to skin a cat. You guys probably heard me say this. Again, no offense to cat lovers, but yeah, it's an idiom or proverb, whatever you call it, right? My daughter loves cats. I never use this in front of her. Okay, so the other way to look at this, same equation. So when we know that this is 10 volts, when we know that this is 1 volt, we know that we're gonna work through it. That the net current is gonna go from the 10 volt to the 1 volt, right? So this is basically gonna be the direction like this, right? And I taught you guys that, and this is 1 ohm, right? That current enters the positive terminal of the resistor and leaves the negative terminal. Another way to write this, some students find it very, very easy. So let's call it current I, right? Current is entering the negative terminal of this battery. I'm going to simply write this voltage drop as, and we are really getting into KVL. This is not really KCL, this is really KVL, right? So I encountered the negative terminal of this voltage source, right? So I'm going to write this as negative 10 volts. Make sense? I encountered the positive terminal of the resistor when the current is making a loop. I'm going to write this as positive 1 ohms times the current. Make sense? I encounter the positive terminal of this 1 volt, and I'm going to write this as plus 1 volt. Make sense? And set it all equal to 0. Okay, so you're going to see how this is going to shake out. The only negative is this guy. I'm going to bring this out here, right? So I'm left with 1 volt plus 1 ohm times I is equal to 10 volt. This is another way to write it. It ended up being the same thing. You ended up having the voltage gain on right-hand side, or right-hand side in this case. Right, left doesn't matter, right? On one side and all the drops on the other side. Again, multiple ways to skin a cat, guys, but you need to know your basics. You need to know your fundamentals, okay? If you know the fundamentals, you're going to be dealing with this very easily. Okay, so let's dive into some practice problems. We have, KCL, KVL also to deal with. So the way I work through these problems in live training essentially is that this problem has already been solved in the on-demand. We're going to just look at it more broadly, right now, and learn essentially the concepts over here. So the way I teach in live training, on demand is a different format. So it's one directional, obviously, and I have to cover tons of content, right? So I'm a little bit more robotic, right? I know what I need to deliver in shortest amount of time possible. With the feedback like we are having right now, it helps us explore 360 degrees of the concept. So I typically embed these type of questions that you're seeing over here in my live training. Okay, so let's cruise through this. Now, the first question is, which point in the circuit qualifies as a node? I'm going to mark them, okay? Which one of these are nodes? Quickly, guys. B and C, most of you guys are saying B and C. Yeah, fair enough. So let's look at it. Okay? So B can be considered a node because it is connected to two different points of resistor, essentially, right? So you have B and C different. They're different nodes. Okay, the right way to say this is that Wasim, C and D are one node, same node. Exactly. C and D is basically the same node. Okay. A, B, and C, D are three different nodes. How come? Well, over here at A as well, this point, right? You basically have a different voltage level. At this point, you have a different voltage level. At this point, you have a different voltage level. At C and D, you have the same voltage level, right? So in comparison, you can say that A is a unique potential point, B is a unique potential point, C and D are unique, but same, right? Unique with respect to A and B, but the same. And then what can we say about this guy? What is this? Now, some of you guys are jumping to ground. You guys, reference node, right? The correct way of calling this is a reference node, a common node, or a virtual ground, not a ground, guys, virtual ground. Why is it not a ground? Did I use the symbol here? No, I didn't use the symbol of ground, right? So it's not a ground. It's a virtual ground or a common node or a reference. Okay. Which point should I use? In fact, there's a correction in the statement that I made. Which point can I use as a common or a reference? Which node can I use as a reference? What do you guys think? Anywhere. Yeah, anywhere. I can consider this as my reference point. I can consider this as my reference point. But which point makes more sense? How do you select a virtual ground to make your life easy? Is there any criteria? We're not trying to solve this problem. We are trying to analyze how we go about solving circuit generally. A good criteria, good fit for virtual node is basically that junction where a lot of nodes are combining. BC is fine, right? But you can see that this guy is most definitely the single most common point. So it's the best candidate. Okay. And how does it help us analyze the circuit? Because we can consider that as a reference. We can consider that as a 0 volt, right? And solve the entire circuit accordingly. It's not a problem. Where should I write the KCL equations? So KCLs essentially are going to be written over here, right? B and C. Okay, so these are your true nodes. A is a different potential point, but B and C are your true nodes, especially when you consider this as a reference. So once I set up the circuit like this, then B and C becomes my points where I'm going to write the KCL equation. Is there only one correct assumption for current direction? What do you guys think? This is a loaded question. A lot of students, when they're analyzing circuits, they're like, okay, I need to somehow, pick the right direction of current. Otherwise, I'm going to mess up the circuit. What do you guys think about number 4, guys? Is there only one correct assumption? No, you can select any direction for the current. There's one that's more reasonable than the other, right? There's one that's more reasonable, but at the end, if you get a negative answer, negative with your current, you just flip it. Not a big deal, right? 9 volt. Let me tell you some tips, okay, quickly. If this is a 9 volt battery and this is the only battery in the current in the entire system, it's the heart, right? It's the heart of the circuit. It's what's gonna pump blood throughout the circuit. Correct? What do you expect current is going to be doing? Is it going to be coming into its positive terminal, or it's going to be leaving the positive terminal? What do you guys think? Exiting. So if current is leaving, let's fix this, right? Now, when current enters this node, and I've assumed that this is a virtual node, where do you think that the current is going to go? Through the 6K resistor. Do you expect the current to be coming out of the ground and into the terminal? Or you expect the current to be branching down towards the lower voltage? It's going to go towards the virtual node. Right? So I'm making educated guesses. When there are two power sources, because how we saw, right, when we had the V1 and V2 connected, right? Whether current was going to enter into V1 or V2 was a function of which of those two sources were the bigger one, okay? And then when you throw in multiple circuits in between, then it becomes how the voltage drops are occurring along the circuit. Does it make sense? But when we have only one voltage source or one current source, generally speaking, it's very easy to get, right? Yeah, so the way I can word, I agree with you, Michelle, right? I could probably word this problem, question a little bit more clearly. Obviously, there's only one correct answer, right? But the point is that is your assumption, one assumption that you're going to make is only one single assumption going to lead you to the correct answer, right? That's basically what I'm trying to say over here, right? Even if you flip all of these currents, you'll still end up analyzing the circuits, right? And coming up with the right answer when you make the adjustments with the negative sign, okay? So yeah, strictly speaking, you are correct, okay? But that was not what I was trying to say, okay? So this current is now basically gonna branch out. So when it branches out in here, again, it's gonna branch out like this and it's gonna branch, okay? Does it make sense? Now with the KCL, KVLs, we run into multiple equations and this and that. So for those guys, please use a Casio and TI-36 Pro, right? I think that's gonna be helpful, all right? So let's quickly write these equations. We've already done this in the on-demand course, right? So I'm calling this as VA and VB, right? I assume that the current is going to be going from here to here. This is my virtual node, right? So the current that is, and then the current is going to go like this, and the current is going to go like this, and the current is going to go like this and this. I'm asking for I naught actually over here. So the first equation I wrote is for I naught, right? I naught or I0. This is going to be VB, right? So this is VB, right? Current is flowing in this direction. So higher potential is VB, and the lower potential is 0, right? VB minus 0 divided by 2K. Make sense, guys? Everyone is clear about this, right? High potential, low potential difference divided by the resistor, okay? At node A. So this is my node A, right? So this is interesting. So what I do is I collect all the currents that are entering into a node on one side and all the currents that are leaving on the other side, right? So I have 9 volts minus VA divided by 3K, 9 volts minus VA divided by 3K, right? This is current entering A, right? And these two currents are leaving A, right? So that becomes VA minus 0. So this is VA minus 0 divided by 6, okay? And then I have VA minus VB, right? Divided by 2K. Everyone can see that? These are the two currents that are leaving, correct? Right? Any questions? Please ask. If it's obvious, we can move ahead. So at this point in time, how many unknowns we have? I have an unknown in the form of VA. I have an unknown in the form of VB. I have an unknown in the form of I naught. So I have 2 equations and 3 unknowns. I need to create one more equation. And that's going to be by writing at node B. Okay. At node B, I have, now the thing is that don't arbitrarily flip the direction of this current when you write KCL at B. We got to stay consistent. This is the second mistake. Remember, 25% of the circuit mistakes are analysis problems. Students are not able to determine VG and VD, voltage gain and voltage drop with respect to voltage sources. The remaining 25% is by changing arbitrarily the direction. So whatever directions you assume, right? I assume the current is going to be doing this. I'm going to stick with this throughout the circuit analysis. I'm going to write every single equation that is consistent with this assumption. If halfway between writing node KCL at A versus writing node KCL at B, I end up, becoming wishy-washy or lose track of my assumptions, all bets are off, okay? So the remaining 25% is arbitrarily changing the direction as you're going along, okay? So when I'm writing KCL at node B, notice over here, the directions were assumed to be this, right? That's how I wrote my KCL at node A, right? So I got to stay consistent. I got to push the current from A to B, right? So that becomes VA minus VB divided by 2K. This is the current that's entering, and I'm going to take these currents as branching out of B, right? So that's VB minus 0 divided by 2K, VB minus 0 divided by 2K. Make sense? Now, when we step back, we see that I have I naught, VB, and VA, 3 equations, 3 unknown. Punch them in the calculator, do back substitution, use matrices, whatever you want to do, right? Solve these equations, right? It's pretty simple once you get to this point. Your actual test is coming up with these equations correctly and consistently with your circuit assumption. The rest is math, okay? Don't get fixated on the math. This is the key point. Does it make sense, guys? Is it clear? All right, so we have 3 equations, 3 unknowns, and then we can solve them using the calculator, back substitution, whatever. The math is irrelevant, okay? The math is not the focus over here. The focus is how we crack these problems, right? So in KCL, be mindful of your circuit assumptions. Make your equations talk to your circuit and vice versa, okay? Don't arbitrarily flip the direction of current, okay? While writing at node A versus node B. Very common mistake. All right, guys? Make sense? All right, let's move on. Now, this is a problem in which I have a voltage source and a current source already solved in the on-demand program, but I'm just going to look at it more holistically. Okay, is a 3 volt source a problem in this circuit? Can somebody write me an equation? Can somebody write me an equation for the current that is flowing through the 3 volt source? Can we write an equation, guys? Take a stab at it quickly. This 3 volt is a problem. Why is a problem? Why is this a problem? We can do superposition. I agree. Yeah, and I'd appreciate if you guys can select everyone in the drop down when you're sharing your comments. We can do superposition, but if I am hell bent on solving this with KCL, KVL type of stuff, how are we going to solve it? And why is this a problem? Did I mention this in the on-demand course? It's a supernode. Okay, this is called a supernode. Remember the VA that I was showing you? So not the VA, but essentially this point, right? So it's a supernode in this case, guys. Why? Because we cannot write a direct equation for the current that is passing through it. It is not practical for us to write an equation for current passing through a voltage source, okay? And it is not practical for us to write an equation for voltage across a current source. This is resulting in supernode, and that results in a super mesh. Okay, so how are we going to solve it? First of all, let's define two voltages, VA and VB. When we are dealing with super node, super mesh type of stuff, there's one equation that is always right in your face. Can somebody tell me what is that equation in this case? The equation that is right in your face. Quickly, guys. What is the equation that's right in your face? Exactly. Yep. VA minus VB is equal to 3 volt. Now, anybody who is not able to latch onto this equation is not going to be able to solve this problem. You can do superposition, that will help you, but not with our KCL's case, KVL. You guys saw how these guys came up with VA minus VB is equal to 3 volt. Why is it not VB minus VA is equal to 3 volt? At the end of the day, there's just 3 volts in between, right? Why do we have to write it as VB minus VA? Sorry, VA minus VB and not VB minus. What do you guys think? Why? Why not VB minus VA, guys? Quickly. You should be able to defend your position, right? It's not just you come up with the right answer. You must be able to explain why you came up with the right answer, right? Positive terminal, yeah. The positive terminal, the higher terminal, the higher potential is connected to VA. And the negative terminal, which is a lower voltage, lower potential, is connected to VB. So the difference is always high minus low, right? That's 3 volts. Now our life is easy. Why? I'm going to just throw a virtual ground over here. How am I going to write the equation for I1? I'm going to say that my I1 is basically equal to VA minus, what is this voltage? Virtual ground, 0 divided by 3K, correct? Okay. And then what is the current that is flowing through 6K resistor? What is the current that's flowing through 6K resistor? Help me out, guys, quickly. Okay, we gotta, now I slowed down when I had to slow down. I'm going to speed up when I think that we should be speeding up, because we've accumulated that knowledge base that we're going to be playing around with, right? Yes, VB, more strictly, it's VB minus 0 divided by 6K, right? So let's see how many equations we have and how many unknowns we have, okay? We have 1, 2, 3 equations, right? And we have 1, 2, 3 unknowns. We can solve it, right? I can write another equation, right? I can write another equation that is at KCL at VA, right? So I have 2 milliamps of current that is coming in, right? On the left-hand side. So that's the current that is coming in. I1 is leaving, right? I1 is leaving. Plus, this is the other current, right? VB minus 0 divided by 6. That is leaving. So I have 4 equations basically, right? So I have more equations than I basically need, and I can go ahead and solve them. So using these equations, right, through back substitution, using the calculator, using matrices, whatever, you can solve them. The important thing is to understand how we're getting to these equations, okay? So VA minus 0 divided by 3K, 3 volts is equal to VA minus VB, right? Writing the equation at node A, right? And that basically is it, all right? So super node can be a trick question. Super mesh can be a trick question. Even if you didn't know that this was a super node, those of you who have practice, those of you who have understanding, fundamentals, concepts are clear, the terminology is not going to bother you, right? So you can deal with that. All right. And when I do my live training, I go through 10 additional practice problems, okay, in the same format with my students as part of the homework assignment. All right. So we don't have time to do that. I'm going to jump into our, so current divider. So just to quickly recap. So current divider rule, somebody mentioned the current divider is not mentioned in the handbook. So we've gone through current divider in the on-demand course in detail. Be consistent with the current directions, right? When you're writing the nodes, and learn how to use the calculator for solving the linear problems, right? So let's quickly jump into KVL now. We've actually laid the foundation. I'm going to skip this because we've already discussed this in quite a bit of detail, right? When we're dealing with KVL, the idea is that the sum of voltage drops must be equal to sum of voltage gains, right? In KCL, current that is entering is equal to the current that is leaving. KVL is based on law of conservation of energy. KCL is based on law of conservation of charge or law of conservation of matter, okay? Real application of KVL is in mesh analysis, and that's the final point I want you guys to walk away with, right? And then we'll be diving into, a review of the strategic discussion. So two very simple things I want you guys to remember. Okay, when it comes to KCL and KVL, we've already discussed the voltage gain and voltage drop. That's one. The other thing we discussed was arbitrarily switching between the direction of the current when you move from one node to another node. That was the second thing. The third thing, guys, please take it to heart, memorize it, is that always keep these loops in the same direction when you write in math. Okay, that is a rule. And to be quite honest, stay with counterclockwise, clockwise, doesn't really matter as long as both are the same, right? Most of the textbooks tend to use counterclockwise. It's sort of a 50-50 split. I don't know what I did in this one, right? Doesn't really matter as long as both of them are in the same direction, right? So use clockwise, use counterclockwise, doesn't matter. Okay, but what matters is that these two guys, the loop currents should be assumed in the same direction. Okay, is that clear? So that's another 25%. So there's only 125% pitfall that's remaining, and that is how to deal with the central node, central branch. How to deal with the central branch. So I'm going to tell you how to deal with that. Okay, let me just quickly see how. Okay, I assume this direction. So let's try these equations in this direction, right? So this is clockwise. Now the current I1, and now we're going to piece the knowledge that we have. So I'm going to write this as positive, negative. I'm going to write this as positive and negative. I'm going to write this as positive, negative. I'm going to write this as positive, negative. And really the unknown voltage V0 is across a 6K resistor. So keep that in mind. And then in between, we got to do something, right? And that something is the remaining 20-25% of the mistakes that students make. All right. So what are we going to do over here, guys? What we're going to do over here is, first of all, write the equation for loop number 1. Okay. Loop 1 and then for loop 2. Okay. So for loop 1, let's start with the 2K resistor. It's easy, right? So current is entering the positive terminal of the 2K resistor and leaving the negative terminal. If it enters a positive terminal, we're going to write it as positive. So it's going to be 2K times I1, correct? Current is entering the positive terminal of the 4K resistor and leaving the negative terminal. So I'm going to write it as positive 4K times I1, right? Now, here's the catch. What do I do with the 6K resistor? Because in the 6K resistor, there's also another current that's circulating, I2. So what you guys need to memorize, understand, remember is that when I'm living in loop 1, I assume loop 1 is the strongest. Okay, so you are living in US, you'd say that, okay, US is by far the best country in the world, right? Somebody is living in Europe, they're gonna say, okay, Europe is like a heaven on earth, okay? Or things don't get better than than Middle East, whatever, right? The point is, when you're in loop 1, you assume loop 1 is the strongest, is the dominant. So what I'm gonna do is I'm gonna write 6K times loop 1 current is the stronger dominant one minus loop 2 current, I1 minus I2. Okay, does that make sense? That's how I deal with the 6K resistor. Is it clear, guys? And then I have a voltage gain or a voltage drop. Should I use a plus 12 volt or a negative 12 volt? Plus 12 volt or a negative 12 volt, guys? Quickly, plus, because I'm entering the positive terminal of the battery, right? And all of this should be equal to what? 0, big fat 0, right? Okay, so this is my loop 1 equation. So issues sometimes over here, issues sometimes over here. Okay, so if you're able to sort of dodge these issues, then you're setting up yourself for success. Okay, loop number 2, quickly, let's do loop number 2. I2 enters the positive terminal of the 4K, right? So I have 4K over here and I have I2 over here. Enters the positive terminal of 6K, I2, right? Enters the negative terminal of 12 volt battery, right? So I'm going to write this as minus 12 volt. All right, don't limit yourself. Hey, you know what, batteries are always positive or batteries are always negative. If you try and analyze circuits like always like this, I actually tell my students, I strongly advise against the use of this word always. Whenever in my life training, a student tries to summarize that was seen. So it means that whenever we are doing this, we are always going to do this. I tell them big no, right? Look at it a case-by-case basis. There's no such thing as always in circuit analysis, right? So don't take shortcuts, okay? Don't develop patterns, okay? That's not how you solve circuit. And then about the 6K, what are we going to do about 6K, guys? So I have plus 6K. Now I'm living in loop 2. I'm living in Europe, right? Europe is a heaven on the earth, right? I don't care about the US, the Middle East, this or that, right? So I'm in loop 2. I'm gonna write that as I1 minus I2 or I2 minus I1. I2 minus I1. Make sense? All of this equal to 0. So again, students can trip here. Some students can trip here. These are mines, landmines, okay? In these 2 steps, you have 4 possibilities of making mistakes. And then you walk out of the exam thinking you did well on circuit. And quite honestly, it's not difficult for an examiner, for me, right, to have options A, B, C, and D entertaining all 4 possible cases in which only one solution is right and the other solutions have actually taken you in different trajectories. So you do not assign positive and no, the center, the node where both currents meet, this is how you deal with it. Okay, is that clear? Does it make sense, guys? All right, and then you solve it. 2 equations, 2 unknown, that's not a big deal. All right, 2 equations, 2 unknown, punch in your calculator and it will spit out the answer. That's not a big deal, right? Okay, and again, some students that get so fixated, you guys have seen, like, I look at calculators. I don't even have a calculator on my desk right now. I look at my calculators as a tool. They're never going to be able to replace. The only thing that's probably going to replace us is ChatGPT. Okay, that is just super smart. I mean, I'm just completely dazzled by what ChatGPT can do. It apparently took a MCAT exam, USMLE. If you guys have doctors in your family, you would know it's a part 1 that you have to take, part 1, part 2, and it aced it. But the calculator, at least the resources that we have on the exam, they are just dumb tools. Okay, so don't get a false sense of confidence thinking that, hey, I have calculator and I have the handbook. You know, it's like legalized cheating. I can actually go and find answers in the handbook. My calculator is going to help me solve these circuit analysis problems. Unfortunately, it won't. It will just give you a false sense of confidence. I don't consider, the mathematical portion of circuit analysis to be the place where students make mistakes. You can still make mistakes here, but that would be on you, right? Completely on you, right? Well, this is on you as well. I mean, if you don't put in the time and effort to learn the concept, but this is crucial, right? Because it will come up and again and again and again in electronics. It will come up again and again in power system. It will come up, a billion times in PE power. Okay, so let's do this one quick one, guys, and then we will get into our Q&A. So over here, when we are doing mesh analysis, this actually is very easy, right? This is very easy. The issue is that I'm asking you to calculate voltage across the current source. What did I tell you just recently? We cannot directly calculate a voltage across a current source, and we cannot calculate a current passing through a voltage source directly. Okay, so when I write my loops, first of all, both of these guys have to be equal. I mean, the same direction, correct? You cannot make one counter clockwise, the other one clock. Okay, all right. The other thing is that what I need to do is handle this current source. Can somebody tell me what this current source, whether it's going to help me or hurt me? Yeah, David, you're right. So what would that mean? How are you going to write it? Quickly, guys. Remember, I don't ask my students to sort of rush in PE power exam because they have 6 minutes per question. For FE, you need to connect the dots. And again, please remind me, if there's one question I definitely want to go in detail, is about time management. It is very close to my heart and is one of those things that, almost annoy me. Irritates me when students ask about time management and then they have different theories. I have a very strong opinion about it, and I'm going to share that with you guys. Okay, so I2 is equal to 2 milliamp. So those of you still scratching your head, you know where you're going wrong. You're not going wrong with your lack of proficiency in calculator or your understanding of familiarity with the handbook. You're going wrong with your conceptual theoretical understanding. And if you're not able to latch on the fact that I2 is equal to 2 milliamps, no matter what trick you use in your toolbox for time management, it's not going to help you. Whether you flag the problems, whether you do all the solve problems first, whether you do the problems top to bottom or bottom to up, it's not going to make up for the lack of theoretical understanding. And those of you who were able to latch on to the fact that I2 is equal to 2 milliamps, how much time you save? Your calculator is not going to save that time. Theory, guys, concepts, first principle. Okay, first principles. So I2 is equal to 2 milliamp, right? Now let's write our equation. So let's write our equation for loop 1. Let's write our equation for loop 2. So let's quickly write for loop 1. Okay. Current is entering the negative terminal of the 12-volt battery. Am I going to write this as positive 12 volt or negative 12 volt? Quickly. Minus 12, right? Minus 12. And then I'm going to write it as 3K times I1, correct? Right? Because current enters the positive terminal of this. And again, the center node is going to be center branch is going to be 6K. So I'm living in the US. US is the best country in the world, right? It's going to be I1 minus I2, right? But what is I2? 2 milliamp. I already know this. 2 milliamp is equal to 0. That's it. That's the solution of this entire problem, okay? Because I have one equation, one unknown, because I already know the value of I2. All right, guys? So we can go about solving that. And then I can ask about V naught, and I can ask about this or that. So in loop 2, I just call this voltage as V naught, right? I already know the value of I2, right? And then I'll carry V naught as an unknown, and I can work through that. That's not a problem. Okay. Is that clear, guys? Yeah. And then I go about solving. All right. So what is the moral of the story? And again, this was supposed to be a 1 hour long session, and we are at 1 hour, 15, 10, 12 minutes, and we are not even done yet. Right. So the moral of the story, how about you guys give me a one line? What is the biggest takeaway from this, 45, 50-minute discussion that we've had on KCL, KVL? How about you reflect upon it? Quickly, what is the biggest takeaway for you? One line only, okay? Don't summarize like the 25% mistakes are made in voltage drop and voltage gain, 25% mistakes are made in this or that. Exactly. Know the fundamentals. FE exam is fundamentals of engineering, okay? Don't take shortcuts. You might pass FE exam, okay, with some strengths, some weaknesses, but some of these topics, guys, circuits, electronics, power, I would love to see you in my PE power program, and it would be to your disadvantage if you sort of pass the exam, FE exam, barely, and then walk into PE power, and then they're talking about fault analysis, per unit system, symmetrical component. Okay. Yeah. So this is the type of discussion I have in my live training program, and students who go through my live training program, it's a no-brainer for them. When they get to PE, they just go directly into on-demand plus live training program. Okay. All right. So let's go through and then KVL. I go through at least half a dozen practice problems in live training with the same approach. Okay.